That is much better. So today I want to think about our tutorial of criticality. And if you attended the last lecture, you might be informed that we talked about criticality. And I noted that this is singularity and the reality. We talked about the role of applications. There is a correlation length that converges, which is sort of the important part, which is the phenomena. And that as a consequence, we get A. And in particular, we talk about quantization. And stabilization. And now I want to ask a question, what quantum fluctuations will do to this picture? And in order to address that in very general terms, let's consider some kind of matter that is not one point, so the characteristic length of the system, the correlation length. And if you know the two chunks of matter of some characteristic size, we know that for quantum calculations, to affect the critical physics that we are going to see, the characteristic size of quantum fluctuations have to compete with thermal fluctuations that give rise to this divergent correlation length. The reason is that this divergent correlation length that gives rise to scaling and universality sort of washes out short-range physics. In fact, that's something you know when you go to a quantum field description or a field theoretical description of a critical phenomenon, which is continuum theory. So you forget about all the lattice physics, and you can do that because the lattice size over the correlation length goes to zero. And so you don't expect that something similar happens with the expression of operations unless they are of the order of the correlation length. And the convergent size in a semi-classical picture for the quantum calculations would be the Victorian wave. If you recall that if the Victorian wavelength is finite and finite temperature, then you see that you can always find the proximity of the critical point. Remember, this is the thermal control reactor, T minus Tc over Tc, where the correlation length is much bigger than the Victorian wavelength. But this argument breaks down when you go to zero temperature, because this Victorian wavelength is something like square root of 1 over the temperature. So this wavelength itself diverges in the limit of zero temperature. And so in the zero temperature limit, the quantum calculations sort of have enough range to affect the classical process. And so quantum replacement machines then take place at T equals 0. This is not to say that microscopically, at finite temperature, quantum physics plays a role. You know that if you look at the superconductor near Tc at finite temperature, that's a quantum phenomenon. But this is not what this argument is about. It's about whether or not the quantum fluctuations will affect the critical physics, in particular, the critical storms. Okay, so that's the setting. And last time we talked about very general accounts. But for today, I want to take a particular example, a very simple example, and try to look at various limits and extract some of the properties that they expect in a quantum critical form. And the model I'm going to choose is the transfer speed icing model. And it has a component that goes as follows. So we sum over clear neighbors on some letters over these spin operators and on this here. And these operators obey computational principles, which are as follows. Which is such that if they are on different data sites, so if I is Stefan from J, then they will converge. But if they are the same data site, they obey this financial part. So this is the exponential unit. And then we can write it like this. And for simplicity, then we also write this in a slightly simpler form. Then we have one people. Which now makes this complete constant G dimensionless. And we also chose H0 and H1. And the important point that you immediately notice is that H sub 0 and H sub 1 do not commute because of this spinantial part. Okay? And keeping in mind what we just discussed, I'm going to, at least for now, stick at T with 0. And if you approach 0 temperature, then you know that the free energy goes over into the ground state energy of the system. And everything is true. What we said, then you expect that for the quantum phase position, we see some sort of singularity in the ground state, which means that it may be a continuous function of the position, but the derivatives may not be circular. Okay, good. So we go ahead and consider what the ground state matter could be more than one. And for simplicity, let's take this system and look at two cases. Let's look at the case where G is equal to 0 and contrast this where G approaches infinity. Okay? And so if we forget about this part, then we only deal with H sub 0. This is essentially a nice model. So we know that the Hamiltonian has a spin inversion symmetry, or so-called S2 symmetry. And we have two ground states that the system has at its disposal, that we run them as either this, where we sum over all, so we take the product over all n sides. Either of spins are up. This is the eigenbasis of sigma c, or they may all be down. And the system will pick one of the two. So this is contains the broken down, this is the symmetry of the Hamiltonian, and we can sort of by thinking of a magnetic field so this is not this transversal field I'm thinking about. I'm thinking about coupling some H sigma C to the system, then taking the limit from above, and that will specify one of the two ground states that I will get. So let's say I'm interested in the following matrix element, and I go to the description. Then I know I will get A, sigma A, and you see that this is one. Let me. So imagine that what I'm writing here now is meant to be below, but I don't want to squeeze it in there because, will you see it if I write it here? Okay. So, and you can also sort of calculate the relation function, let's say, and this will be one independent of how far I and J are apart. Okay, so clearly, if I and J is the same, then you invoke the alpha, you get one, but think that they are apart. They're on the states, and then you get one independent of the distance. So that's what happens at G equals 0. Let's look what happens when G goes to infinity. Then we essentially forget about this part, and we want to maximize this part of the Hamiltonian. There's spike sign here. And that means we look at the eigenstates of sigma x, which is where the eigenstate of sigma c can be written as, say, about it like this. So it's the sum, second one. Difference like this, and so what we get is the product of this state on this side as the constant. Okay. You see that there's a normalization factor now of 1 over 2 to the power n², and what this tells you is that the ground state in this limit is a coherent superposition of all possible. Yeah.
I just curious because usually from 0 and I think A state A plus state B, the superposition is all is from state B from 0.
Yeah, so in principle, you can do that. I want to specify that it's only the one of them. Okay.
So that means G cannot be exactly equal to 0. We should keep a very, very small external field.
No, I mean, if you put G into 0, what we have is a standardized normal, right? So you can consider that limit. That's perfectly fine. Okay, so let's look at G to infinity. Here we have the superposition, the coherent superposition of equal weight states of all possibilities of spin up and spin down. And so if you exchange this, then the system will, the state will be invariant. And that's a statement of it being disordered, but it's quantum disordered at t equals 0. And if you now calculate this matrix element, if this is a ground state, then you do find this is 0. And if you look at this matrix element, this sort of correlation function, then what you find is that is 1 if they are the same, and it's 0 otherwise. But so the same that we have here, it's independent of how far they are apart. So it's independent of the distance, how far you take them. But this second property is only valid in the limit that g goes to infinity. That will no longer hold if g is finite but large. Okay? And yeah. All right. So this is true independent of the dimension that you look at. In the following, I want to go and ask what happens if we go slightly away from g equals 0 or slightly reduce g in the vicinity of this strong coupling fixed point. And we will do that in one dimension. Okay? So let me now consider that we have a chain. We go to one dimension and then we consider the transport icing chain. And we want to ask now what happens if G is finite, but it's much less than 1. And so the question then is starting from this state designated as A that I just had, what will happen? And in order to address that, let me first note that if you start with this state and you introduce spin flips, then you have to pay an excitation energy, and this excitation energy delta E. So what I want to consider is, let's say, we stay like this. Then since you have to create 2 bounds, you have this excitation energy of 1. And it turns out that at least if we take a finite system of n sides and we choose open boundary conditions, then it's easy to see that there is an even lower excitation group available to the system where we only create 1 bound, which is something like a domain 1. Okay, so this has also let me say this is 2, and then this is the next one. So this is as expensive, which you can think of as having this single particle excitation as having 2 domain balls coming together. Okay, and so the lowest excitations and that we have in the system where G is tiny are these domain balls. Okay, and now we want to ask the question: what is the effect of this part of the Hamilton operator on these domain balls? And this gives you some effective Hamiltonian around G equals 0. And then you can ask you try to diagonalize this, and you can ask what happens to the excitation energies. If you do that, then let's first address what happens when you apply the sigma x operator to a state like this. You have then physics that we might so let's say we have a state that has a domain wall, and between I and I plus 1, So we start with inside. So this is something like the state. And then we want to understand what if we come with the sigma x operator and act on such a state. And there are two possibilities. Either this state acts far away from the domain ball. This is the domain ball. And then, okay, this operator is sort of a states. Something like this. And so if now sigma x at j acts on this state far away from the domain ball, where we will get this, it will, let's say this is j, and this is far away, it will simply flip that spin, and we have to play two bonds, and that costs us a certain energy. And we completely will ignore that. The second possibility is that we act near the domain ball. And in that case, see, given that sigma x simply spins, it moves the domain ball, either to the left or to the right. Okay? And by what we just noted, this is a much cheaper excitation. So these are the low energy excitations that we want to keep and want to build your effective Hamiltonian out of it. And that then will be diagonalized, and this gives you a picture of what happens near g equals 0. If you then act with, so this was one out of our n sigma x that we have. If you consider now what H1 does onto the state, then you find then you have two possibilities. It shifts your domain ball, and there's a prefactor of your G, something like this. Now, you also want to subtract the bound state energy of this. This then gives you an effective Hamiltonian, and then you go to Fourier space to diagonalize this. And that gives you the spectrum of the excitations near the point where G is. So this leads to an excitation spectrum of the following form. So let's say this is and the local energy you have at k is 0, and you see that there is a gap as a function of g, which goes like 1 minus g minus 2. Yeah. And that suggests that there's something at g equal 1 where the gap seems to close. And saying seems to close because we should keep in mind that this is an analysis that is valid for very tiny g, and it's not clear that this will hold true for any finite g. Okay, but that's what we can do. And now you can do the same thing or a similar thing around the state for very large g, for g to infinity. And this by and large runs very similar. Or just that. let's say we want to have G very large, but 1 over G, so 1 over G is tiny by 0. And in that case, we had a superposition of all possible states in the Fourier independent. And to and as our ground state was something that looked like this. On the end. And now you again ask what's the lowest possible excitation that we can have. And it turns out that simply flipping the state. So we'll say now the state is one. Flip. And then continue with the state as before. And then we have to ask, so this has the excitation energy, I think, of your 2G. Could argue that, oh, but G is very large, that's right, but we look at the differences. And we now ask the question, so we have sort of satisfied this part of the Hamiltonian. We want to now ask what's the effect of H0 on that state where we have a low energy excitation. And then the argument is essentially one the same. So we first need to understand what's happening if we apply sigma C to this state, and you see that so we apply so in order to figure out what happens, we want to understand what is the effect of sigma C on such a state. That's easily figured out, and you see it simply gives us this state, and likewise with the other one. Okay? So knowing this, then we can figure out what's the effect on this state with this part of the Hamiltonian. And so what we get is if we apply H0 now on this lower energy state, then we find that the action is actually similar to what we had before. It shifts the position where the excitation occurs. And then there are higher energy excitations of some single multiplication. So thus states resolution is inverse. And then you can do the same as before. You can go to the metric space, you diagonalize this Hamiltonian, and you will find that now this effect of Hamiltonian looks like this. That we scale K, and now you see there's again an energy gap. And K is 0, and it also predicts that this gap vanishes when G goes to 1. Okay, from this side of the problem. Okay, so what we have kind of done so far is that there's G. We haven't really talked about temperature at all at the moment, but we looked at the problem on this side. we looked at the problem on this side, and both calculations or approximations suggest that there's something happening when G is equal to the second thing that one can obtain from this segregation using this side of the problem is that if we now look at one quantity which we calculated at the beginning of this lecture, which can serve as a model. Then for G equals 0, given the side, this was obtained, this was giving us the value 1. But now we see that as G is finite, but we are still on this point where this calculation applies, then the fact that we get domain walls brings down the value of the magnetization, but it will still be finite. And on the other side, what you find there is that if you look at so this is now the final G front state. So we are on the side where G is larger than 1. Here, we said before that this was 0, and this is now replaced by a decaying exponential of the form I minus J over a characteristic length, the coherence length. And this becomes 0 deep in the limit where G goes to infinity. Okay, but for finite, well, largely this is what we have, where C is the correlation length. And I'm getting a step ahead of myself. I should have made a remark I'm going to make first. But if you remember the correlation length we had before that, in terms of the thermal tuning parameter, was defined like this, when V was the correlation length exponent. What one now finds is that we have a minus GC over GC, if you wish, and it goes like minus nu, and nu turns out to be 1. This you can obtain because for this particular problem in one dimension, there's actually an exact solution. Okay? So in some sense, you could forget about what I just said. We could right away go to the exact solution, which uses a transformation between spins and fermions. And that is called the Jordan-Wiener transformation. I'm not going through this in detail, but I will quote the Hamiltonian that you end up with. So for this particular problem, we can do what is called a Jordan-Wiener transformation. To split as fermions. The Hilbert space of spins is finite. The Hilbert space for the spin and a half problem is finite. So that's one of the inputs. The other one is that we have a fermentation relation, and that leads to some complications. So you get something like strings attached to the fermions. But if you do that, then for this particular problem, you do this into some rotation in spin space, and then you get an effective. It looks yes. And see that it's a non-linear problem, but we get a quadratic terms in the Fermi creation and deviation operators, the C diagram you see. And you also see a CI plus 1, so that suggests you go to the event space to diagonalize the problem. If you do that, you find this following. This form. And now you could compare what happens when G is very small and what happens when G is very large. Then we have this one. And you see that this reproduces both of the cases that we had before. You also see that when case is 0, then we have a you see that this rate is 2, 1 minus G, and you see that we have functions for G equal 1. So the approximations that we did before, you can extend them all the way. And you get close and she see equal to 1. And if we go now to what I just introduced here, then this was the correlation length as a function of now the non-thermal tuning parameter. That's how it's usually called. Because remember, we are at T equals 0. We look at the transition as a function of G. It's no longer temperature. But the form is the same as the one we had before. Here is this energy gap that closes at the critical point. And since this is energy, the inverse will be something of dimension of time. And so let's call this C tau. And as the approaches GC, the gap vanishes. So this this length in time diverges. Now, what is the significance of this? This tells us something about the spatial correlations, right? And minus J, as we approach this particular point. This tells us something about correlations in the timeline direction. Okay. And so if you wish people space, but timeline correlations. And to compare the two, you can introduce a exponent that relates this temporal landscape to the spatial one. So this was the inverse of the gap. And now we relate this to the spatial correlation length via some extra critical exponent. And this one is called the dynamic exponent. And written like this, you see that it tells you something about the symmetry of these two types of fluctuations. So it tells you something about the symmetry between time and space. With respect to the calculations. Okay, and since we know how to write the spatial correlation length in terms of the correlation length exponent nu, we immediately see that we can write G minus Gz, and then we have minus nu. That's but if you now compare this with our result that you obtained, you see that nu times c has to be 1. Nu equals 1 we already have established. So for our problem here, we find that set is equal to 1. So the calculations are very simple. Okay. Now, since this is an energy scale, we can also compare it with temperature. So this is G, this is Gc, and here we have our order problem. This, and there are some explanations. This form, on the other side, we have a state that is characterized by this type of spin flips. At least deep on this side and deep in the face. And then there is the vanishing of the energy gap. And you can compare this now with the temperature. So the thermal energy might be much smaller than the gap than you are on this side. Here, the system is in a state where, because of temperature, it cannot really tell whether you are right at the critical coupling or slightly off, because the sort of fluctuation spectrum is cut off. And that's and there's usually some high energy cutoff where all these power laws are no longer valid because we get non-universal features. And anything else that you say? Yeah, so we will see in a little while that if you write down a general action for a quantum problem, that you get dynamics in this, and it typically leads to something of this form. And you see that at zero temperature, this is an extent from 0 to infinity, but at final temperature, this is sort of cut off. And this is related to something you might have heard before, which is that in this quantum critical region, the physics is essentially that of finite size scaling, where the direction in this temporal direction is now finite. It's limited by the extent of this integral. Okay, so I come back to this, but in this region, this is very similar to what we had last time when we looked at the limit L to infinity. At the critical temperature, now we are at critical temperature, and so the fluctuation spectrum is sort of affected by the system being finite. And so quantum critical physics is like, in some sense, in a very real sense for many systems, finite size scaling. Okay. All right. Yeah, so that's now in order to move towards something, so I'm not going into field theories so much, but I want to derive something which I think for this model, which will kind of bring us to this, which is the relation with classical phase positions and the classical mapping. And for that, let's go to, so we started out with something in giga-dimensions, then we went to the transfer speed iso chain in 1D. Let's go to a zero-dimensional problem. Look at the zero-dimensional transfer speed Ising model. There we have a Newtonian that should look like this. Okay? And write down which is the trace of this operator, and this also is some tiny epsilon in power m, where now epsilon is beta over m. And then I can also write this as let me write out the trace. So now I want to, so I write this program out and I insert many resolutions of unity in strict space. And I think, well, let me write it out. Then E minus epsilon gamma sigma x minus epsilon. Oh, there's a minus here, and here. So I get a plus here and a plus here. And so that's sigma set. Now, you know that I did something which in general is not valid. I need beta and the Ross law. The commutator is a number. So I get corrections of all the epsilon squared, and epsilon is small, so I okay. And then there's small. And that repeats. And since I now calculate the traits, I must have a figure of boundary conditions. Conditions. And I can simplify this problem a little further because it's easy to write down this kind of matrix, which is, well, let me call this T1 and T2. I hope we can sort of see what where I'm going and what I'm trying to write, even though I'm sketching. So T1 is this one, choose this, and there's still sort of the product. And then T2 is easy to write down. But T1 is not. So instead of calculating what that is, let me use again the fact that epsilon is very small. So I can write this as gamma sigma x plus epsilon squared. So this is nothing but 1 epsilon gamma, epsilon gamma 1. And so these are the things I should plug in. And the hope is that if m is large enough, that's still really exact. And let's compare this now with a different matrix in the spaces, which is, let's say, K times sigma C and I, sigma I plus 1 C. And remember, this is the H0 essentially of our transfer speed Ising model. Okay. So if you write this down, what you have is now E minus E plus A minus 1 And let me squeeze in the next step here, which is not pull out one, then one, two, three. Okay. Okay. So having done this, we can now compare the two and ask what is K. And you will see that in order to make this relation perfect, you choose K as 1/2 log epsilon gamma. And then we replace this part, sigma x, by small t1. And if you then follow through with this, what you get is what you get for this. So all you do is you connect now. You get a prefactor from this part, which somehow should sense exponential lot, which is exactly this one, 2 power n. And then we have the trace. So we have still T2. So what I'm trying to say is before we said we have T1, T2, I want to write this now as trace T1, T2, where C2, the small T2 equals the large T2. And for T1, I just showed you that I want to replace these. Okay? And then if you take everything together, you find that this is now the trace of a one-dimensional Hamiltonian that looks like an icing. So. What we have shown is that our zero-dimensional transverse field icing model is completely equivalent. As long as we understand by calculating the trace to the one-dimensional icing model. Okay? So we went from something that is random to something that is classical, but that lives in a dimension which is the original zero-dimensional problem plus 1. Okay? So you go from a theory that is 1, 0 to one that is 0, 1. I guess that's the theory. Okay. And this is essentially what is called the classical mapping. You can do the same thing. So the zero-dimensional transverse icing model becomes the one-dimensional basic model. And if you would have started from a d-dimensional icing model, you would have ended up with a t plus 1 dimensional icing model. And more generally, this is the statement. So this one that we have here, has to do with the critical exponent being 1. More generally, what we would have is that the package dimension would be spatial. All right. So, and with this, one moment. With this, you could now write down the theory for this problem. Which is that whenever we have the gradient in our problem of spatial fluctuations. Okay? This is something that you go from Landau theory to Ginzburg-Landau theory. This measures the path of spatial fluctuations. Right. And so this now we have to come with the company by a part that reflects the temporal fluctuations, and since that is one, this is simply this. So I might know something now, but either what we just discussed, what he makes this. If you are not convinced, you could have taken the Hamiltonian and you could have found the isotopic coupling, and then went through the analysis for this coupling field. So this is then how the problem looks. In higher dimensions, we have to break. Then there is the part that in general we would tune that signals the direction of the massive field. And then there's interactions, which could be either in this form. Something like this. And you see, this is the quadratic part of this problem. You identify the inverse of this quadratic part as the Green's function associated with the problem. This is the interaction part. And it's living in E plus 1. But the T plus 1 or E that you see here, for this, you really have to look at how the different fluctuations enter into the problem and how you have to scale them. Okay, to get something that looks isotropic and then becomes the problem. And if you look at this, this is a factor field. This is easy to identify because and everything we said about this last time now still applies. There is an upper critical dimension, which now is 3, because we have the E upper critical dimension is 4, but this set is equal to 1. So the physics below 3 dimensions is governed by entanglement. But of this is about theory. And in particular, in 3 dimensions, it's and you can now look at quantities. Let's say we look at a quantity that goes like G minus GC or GC to some exponent Y. Some quantity, some quantity small. Then you can ask what's the scaling form of this, and if we are below the critical dimension, then hyperscaling relation solved, and in that case, you find that the proper, I think call it X, then the proper scaling form of this will be so we now look at dynamics, and I come to that later. Let's just write down what we have. So this is related to the free energy scaling, the finite size that we discussed last time. And what we get for that is then that it goes like E minus GC over this putative exponent Y, and then there's a scaling function, which may distinguish whether or not we are above or below. And then we repeat, let's say this is again G minus GC, new set over T. And then there's formula over T. Okay, and so there is what one would call omega over t scale. But if you derive this, you will have to use hyperscaling because, in a sense, and that's the remark I was thinking about making, but then you are relating a correlation function to something which is a free energy. And that's where hyperscaling relations have to come in, or something like the fluctuation dissipation theorem. Okay? All right. So that's that. Now, this is so far the transverse field icing model, and I think this lecture is essentially over. So I'll just make a few remarks, and then we go to the slides. But I might now need another 5 minutes or so. One remark I want to make is we could have started with something more. And let me make another remark first. Sticking still with the transverse field icing model, because in principle there is also order in higher dimensions, higher than one, which ranges. Let's see how bad I'm drawing. Which ranges of the critical point. If you are not in the problem that you can solve exactly, the finite temperature problem is below the lower critical dimension. So fluctuations will be so strong that order cannot be left. And then you get this simplified picture. So this is 1D, and this is higher than. Okay, so that's one remark. The second remark that I want to make concerns in field theory. So let's say you start with this with some Hamiltonian, and you want to analyze it. So you get it right. So we could have started with many different Hamiltonians. For example, something that would look like a both model to analyze the display transition, superhuman transition. And then we would sort of, it's not, since I have here, write it down. And so they have interacting parts and non-interacting parts, and then you go to some functional integral version of the partition function. So let's say that we write this in terms of some Bosonic field. If you think the Howard model, you keep it Fermi. So in order to write this in terms of Fermi fields, you have to work with the Howard, but you can continue that instead. And then you get the action being the integral over the in there, then you so what's something like sharing this form. So intelligence is related to how we started in the first class, which is in the Johnson transformation. It's central. And then you can try to analyze it. For the spatial decrease, you have a sum over them, which will enter as an integral, a d-dimensional integral, the fields involved, and then you have what we saw before when we looked at the field theory for the transverse field icing model. Now, what usually can do is you have periodic boundary conditions in imaginary time because we can't find traits, and then we go to mathematical conditions. So that's the remark I'm trying to make. You go to about frequencies. So these are for those, sorry, if you have never heard much about frequency, we have to the boundary condition in time. And so if you now make a Fourier this, it's only certain modes can. And in Fourier space, it's time, so the Fourier transform leads you to frequencies. This the spectrum of possible frequencies in the modes are these possible frequencies. And they are the following. And over there. Now, one problem when you go and start with some RG is that this is a discrete spectrum, especially if it's a continuous, but here it's discrete. However, if you go to zero temperature, that problem goes away because now you get an integral over all frequencies, they become continuous. That's one remark I wanted to make. The second remark concerns once you start with this, how would you recover finite temperature phase positions? Okay, so we started out with all the dynamics, we put it in and said that T equals 0 is there, but how would we recover something that gives us finite temperature position? Right? Let's look at the 0 1-to-1 frequency. So n is it's 0. Plus minus 1, and so on and so forth. And I will say it's L, and here I have this. So this is L, and then this is L. So the 0 is 1 is 0, and if you do the back transform what you have for your field, let me include now spatial increase. This will give you the rate of the 0 on the 0 boundings, see the switch to 0. And you see this average over all the configurations along power. Okay? And it turns out that if you now are finding temperatures, it's only the 0 bar frequency that matters. Okay? You can forget about the others. Essentially, you can shift them to infinity because it better goes to 0 than the high temperature limit. They go to infinity. And so you only deal with this one. And then you can also think of this as the width of the system in this along this smaller frequency axis goes to 0. Okay, and so the finite size scaling, I mean, everything is from now. This is how we recover the finite temperature. And so this quantum classical mapping operates on what's about frequencies. It's an equilibrium property. Okay? So if you were to ask our elements out of equilibrium to a quantum phase transition, this is not really helpful. You should go to the Kellish and go and analyze the problem. And you might find new things. Okay, so that's one possibility of one could proceed. In particular, since if you are in a classical phase transition, the procedure to look at dynamics, meaning if you have a magnet and you ask someone to do some scheduling near the transition, you get a dynamic correlation function, right? So there is, you can ask these questions even though you are in the classical phase transition. And there's a theoretical understanding how to do that. But what it does is it asks you to first solve for a static problem and then turn to the dynamics which is built around the static solution. And that probably is not the way to think about quantum mechanical problems now. So that's a direction we want to go. And another thing you can do and that have people done in recent years is to think about quantum phase transition in terms of spectral information measures. Well, at least the way I'm trying not to say the way I understand it because I don't want to claim to understand it. But one way I think about it is that if you go back to the problem where G is 0 and G goes to infinity, we had simple product states that we both found. at these two extremes. Okay? But if you go to the exact solution and you write down the wave function, you will see that there is a non-analyticity, just like if you look at the vanishing of the image again. It was singular, so the wave function will reflect this as well. Because on this side, you have a finite order parameter, on the other side, you don't. Okay? And so there's some form of quantum entanglement that reflects that. And so you could ask questions like, what does the entanglement entropy do? How does this describe the quantum disorder state? That's one probability. Another quantity that you could try to throw at the problem is called fidelity. This is not too hard to understand, I guess. So let me write down its definition. So we have our Fermi constant for the problem, and then there's some parameter that we will choose small. And then fidelity is defined as the overlap of the wave function of, for example, our problem, the ground state wave function, at coupling constant G versus, so the overlap between this function and the ground state wave function a little bit away. Okay. So that's the fidelity. And then you can ask, is this quantity picking up on the fact that we have here a phase transition? The answer is yes, but what is even a more interesting quantity to look at is the fidelity stuff. Which, well, we can try to expand this in terms of data and scaling the second derivative with respect to data, and that gives you the fidelity. And if you plot the fidelity of this problem, then you see that it's sharply at the transition. And the advantage why you might want to look at this one versus this one is if you're far away from the transition, the fidelity has to go to zero. If you go to an infinite system, it will go to zero. So that might be a much better quantity. And if you look for quantum information and quantum phase transitions, there is a huge body of literature. Okay, that's all I wanted to say. I suggest we make a 5-minute break. And then I'll show you some slides, and then we slowly go into the late afternoon. Okay. Any pressing question that you have?
So you mentioned this quantum to classical mapping. I wonder if this is always true. That's It's always
it's not generally part of what I'm going to show. There are systems that thanks for raising this issue. So it's sort of the standard theory, but it may not always be true. Certainly out of equilibrium, there's no basis for it, as I mentioned, but there are many systems that have been identified where it doesn't seem to be true either. There are debates about it, that's why I said it doesn't seem to be. And it will essentially be the topic of the slides I'm going to show. Because remember what I said on this slide before, I said that we would expect this only over the scale below the upper critical dimension. And so if you see it, you know your system is critical, that is, the scaling is not in motion, then it will tell you that you are below the upper critical dimension. But since we also said that so we said that the effective dimension is the spatial dimension per step. If you are above the upper critical dimension, which something like 4, it's very easy, depending on set, for a 3-dimensional system to be above the upper critical dimension. And so you would think that for most of these quantum phase conditions, they are downstream. They are not showing calculations that are interacting, or like we discussed in lecture 1, where if you go to bigger and bigger system sizes, the distribution is always broad, it's not falling. So that's what probability scaling will tell you. It's like a diagnostic tool. But because of this, if you follow this procedure, you start with, say, from the Fermi uncovered model, and you want to describe something like spin density wave transition, then depending on whether you have an anti-Fermi, which comes with some ordering wave vector, or you have a paramagnetic, you get either a set being true or a set that dynamic exponent being 3. And so the seeds are basically about, you would not expect probability scaling. But one does see it, and that's the topic in 5 minutes. Okay, so Professor Chung is right. There are exceptions, and there's a big area of research interest. Okay, we come to that in 5 minutes.
Okay, we come back around the 250. Yeah.